All right, so now that we know the type of problem we'll be thinking about, we're going to lay some groundwork for how we talk about solutions to this type of differential equation. So we're concerned with the solutions that we might have. And sort of an important thing to note is we're going to break this up into cases. So we can still have homogeneous and non-homogeneous versions of this type of differential equation we're talking about, nth order linear ODEs. And so the equation I gave you for an nth order linear ODE was like this. All equal to g of x. And the homogeneous version is just going to be all the same stuff on the left-hand side. And I'm not going to write out all that stuff again. Oops, shouldn't have had a y right there. Should have had it right there. Equal to 0 instead. So that's how we learn that classification at the start of class. And I'm going to call the homogeneous equation star and the non-homogeneous equation circle. Actually, that was supposed to be a flower, so I won't call it circle. And the simplest thing to do is going to be to think about the homogeneous equation first. Which I've labeled star. And there's going to be a couple things that we sort of learn our facts about these solutions. So, first fact is if you find a bunch of functions, y1 through yk, and when you plug them into star, the differential equations, they turn out to be 0, or they satisfy the ODE star. Then the thing you make out of these functions called a linear combination which if you haven't heard that word recently, aren't like taking linear algebra or something like that, that's going to be just some y equal to c1, y1 plus c2, y2 down through ck, yk for any c1 through ck. That thing is also a solution to the differential equation, so that it's also going to satisfy the ODE. As long as those c's are constants. So maybe I'll say that right here for constant C1 through CK. And note that sum can be 0. So you don't have to use all of the equations either. If you had like 5 functions, but you took a sum of 2 of them, that would still fall within this idea of a linear combination. And then if these functions have two special properties, then their linear combination forms the general solution to the differential equation we're thinking about. And we're going to write those special conditions right here. So the first thing is that they have to be what's called linearly independent. And the requirement for that is that if C1, F1 plus, C1, Y1 plus C2, Y2 down through CK, YK equals 0, then the constants must be C1 equals C2 equals all the way down through CK equal to 0. So linear independence means if you have this handful of functions and you take a linear combination of them, but you always get 0, then the only way that's possible is if all of your constants were 0. And then I'm going to leave kind of a space there because we're going to define an easier way to check linear independence in a second. But the second special property is that you just have to have the correct number of these functions. So you need to have exactly n functions y to form a general solution. Not collusion, solution. So that thing that I called k before, have to have n of them. Or just you have y1, y2, down through y sub n minus 1, y sub n. So that property is just as easy as counting. And these are, just to like keep everything straight for us, the two special properties that we need to have in order to form a general solution. And right now I'm going to write an easier way to check this first special property because this definition of linear independence isn't really easy to work with in practice. And the easier way to check is going to be that you want to make sure that something called the Wronskian is non-zero. Where the Wronskian is something where you plug in those n functions that you have into a determinant. And in the next video, I'll do an example where you see what a determinant is. But you populate your Wronskian with all of the derivatives of y. until it's kind of a square shape. And if you haven't taken determinants, or this is like iffy for you, don't worry, it's the first thing we're going to do in the next video.